Good evening. Today we are going to see a floor beam, and that is continuous beam. So design of continuous floor beam. Now design a continuous floor beam. So you can see ABC. So we have this beam ABC, and we have to design that beam ABC. So this continuous beam. The depth of slab is 140 millimeter and monolithic with the beams. The beam have width 230, internal beam is there. So generally we have walls 230. So we are going to keep width also 230. Slab carries floor finish 1.5 kilonewton per meter square and superimposed load 4 kilonewton per meter square. Use M25 and Fe415. So we have on ABC, we have load from slab S1, slab S2 and slab S4. So now we are not going to get any load from slab S5, that we will see now. So step 1, effective span. Maximum span has to consider in the calculation of depth. Maximum span means we have two beams. So if we will see, so we have this will be ABC. And then out of this we have to consider maximum as we are in slabs also. So L effective we have 5600 millimeter. Then we have step 2, trial depth, same as we have seen in ground beams and in plinth beams. So D is L effective by 12. So 13 we have taken. So L effective by 13. And then we will get this value as 430.76 millimeters. So we have this as 430.76 millimeter. So this we have taken L effective by 13. Then we have D is equal to D plus 40, 43.76 plus 40, 470.76 millimeter. So we have provided on higher side. So we have provided D 480 millimeter and small d it becomes 40 millimeter because cover we have taken as 40 millimeters. Then load calculations. Now as we have seen in floor beam simply supported, we have same load from slab, weight of wall and self weight of beam. So these three same in your ground beam also. So load transfer from slab to beam ABC is as follows. Now we know we have slab load distribution in this person. Shorter span will take triangular load, longer span will take trapezoidal load. So this trapezoidal load will come on AB from slab S1. So this like this. Now from S2 also we are going to get this trapezoidal load on beam AB. So we have only this trapezoidal. Now if we will go to BC, then we have this will be triangular load because we have shorter span. So on shorter span we will get triangular load and this the load will be on this BC. So you can see likewise. Now for S5 we have one-way slab. So load of one-way slab will be half on both longer span. We do not have any load on shorter span. So we do not have any load there from S5. So we have from S1, S2 on AB and from S4 on BC. Now how to calculate value that we know, self weight of slab 25 into 0.14, 3.5, floor finish 1.5. Now here we are going to calculate the value separately because we are going to use moment distribution method. So now dead load we have to calculate separately, live load also we have to calculate separately. So we have total dead load, we have 3.5 plus 1.5, where we have 1.5 as floor finish, it comes 5 kilonewton per meter square. Now you can see this. So we have loads in this fashion. So now we will have beta, that is Ly by Lx. We have 5.6 upon 4, which will be 1.4 because we have to go formula of W equivalent for this trapezoidal. And we know this formula we have WLX by 2 in bracket 1 minus 1 upon 3 beta square. We have WLX by 2, 1 minus 1 upon 2 beta, that is for shear force. This is for flexure. So dead load from slab to beam. So now we have W we have calculated. If you will see, we have UD we are taking, that is 5. Then we have this value will be 5 into 4 by 2, 1 minus 1 upon 3 into 1.4 square. Beta 1.4, that also we have seen in this. So 5.6 upon 4, we will have this value as 1.4. Then we have total dead load from slab to beam. So now we have trapezoid from both sides, and therefore we have multiplied by 2. We have same slabs and same beta value, and therefore we made it as doubled. Now weight of wall, we have 20 BH, 20 into 0.3, 3 minus 0.48, because we have this is overall depth of the beam, and that will gives me 11.59 kilonewton per meter. Now self weight of beam 25 B into D, and then 25 into 0.23, and then we have B into D. So we have this will be 0.48, this will be depth of beam, and then we have to subtract this depth of slab. That we have to subtract actually. So we have 0.48 minus 0.14, and we will get this value as 1.96 kilonewton per meter. So now knowing these total dead loads, we will add this, and by adding this, we will get total dead load as 30.15 kilonewton meter. Now we will make it factoried. So 1.5 into 30.15, 45.23 kilonewton per meter, as consider it as 45.3 kilonewton per meter. Now we will have factoried live load from slab to beam. We know live load is given 4. So 1.5, this is for factoried. This is W. Then we have Lx by 2, and then 1 minus 1 upon 3 beta square. So same formula we have used, same formula we have for live load also. And by this we will get factoried live load as 9.6 kilonewton per meter. So now we will go load on BC. So we have only triangular load, nothing other than that. And then we will have WLX by 3, 5 into 3 by 3. And that we will get it as 5 kilonewton per meter. Now weight of fall, we have 20 B into H. And then again we have 20 B. And we have 3 minus 0.48, 11.59 kilonewton per meter. Then we have self weight of beam. In the same way, we have same value 1.96. This value also we have same 11.59. And then we will add all these. Gives me 18.55 kilonewton per meter. Multiply it by 1.5. We will get it as 27.9 kilonewton per meter. So we have on AB. So we will have factoried live load. So W 1.5, this is for make factoried. W is 4, Lx we have 3, upon 3 we will get it as 6 kilonewton per meter. And then we will go with table on which we will write all the values, that is of dead load, live load, and then total load. Because we have on beams dead load, or we have on beams total load. Now that we will see how we will go for this. We have dead load on AB 45.3, dead load on BC 27.9. We have these values. Then live load, if you will see on AB, we have 9.6, BC we have 6. So we have these values 9.6 and 6 kilonewton per meter. And total load we have 54.9 and then 33.9 kilonewton per meter. Now we will find bending moment again due to dead load and due to total load, because we have dead load on the beam or we have total load on the beam, and we have WL square by 12, and by using WL square by 12 we are going to get these values of bending moment. So these moments we are going to find out, these we are going to use WL square by 12. So if we will take W dead load, then 45.3 into L effective we know 5.6 square by 12, and here we have total, that is 54.9, and in the same way here we have 3, so 27.9 into 3 square by 12 and 33.9 into 3 square by 12, and we will get these values of bending moment. We will go with moment distribution method, and therefore we have to find out distribution factors. Now we have B, Now A is simply supported, C is simply supported. So we have values that is 3 EI by L for BA and 3 EI by L for BC. And then we will substitute the value. In first we have 3 EI upon 5.6.54 and 3 EI upon L. So 3 EI upon 3, that is EI. And from this we can find total stiffness 1.54, and then we will get distribution factors, and these values we are going to get 0.54 divided by 1.54, and this value we will get 0.54 upon 1.54 and 1 upon 1.54, and from this we will get this value. Addition of these two, that should be equal to 1. That you know, because we have seen moment distribution method. Now we have to go maximum hogging moment at support B. Now loading condition. We have total load on AB and BC. Whenever we have to find out maximum moment at support, then we have to apply total load on both spans of the support, and therefore we have applied total load on AB and BC. So we have diagram in this way. Now we will go moment distribution method. So we have DF joint A, B, then we have member AB, BA, BC, CB, and then fixed moment we have seen minus 143.47, 143.47, and minus 25.43, 25.43. You can see these values we have taken from here, where we have these final moments. So we have 143 for AB and 25.43 for BC, that is for total loads. And as here we have total loads, so we have these values. Now we will distribute the moment at support B, 143.47 minus 25.43. So C values 143.47 minus 25.43, and we will get this value as 0.04 and then 581. So this comes minus 118. Sorry, plus 118.04. So we have to distribute this value, and that value we have to distribute, that is equal to minus 118.14. So carry over we have so 143.47, and then we will get total moments, that is equal to, sorry, we have to release first. We have, as support A is simple support, support C is simple support. So we have to release these two supports, and then we will release it minus 143.47. So 143.47, so it becomes 0. Similarly for this 25.43 minus 25.43, this 0. Then we have carry over. Half values we have taken on this side, 71.74 and minus 12.72. And then we are going to get total moment by adding this. So we have 215.21 and minus 38.15. So actually this step is not there. After this we are going to add this. So we have, this will be 215.21 and then minus 38.15. And we will get this as 0.06, 8 sevens are, 4 sevens are. So we have 177.06. And then you can multiply it. So once we have to multiply it by 0.35. So multiplying with 0.35, we will get value as minus 61.97, and then multiply this value by 0.65, and by multiplying by 0.65, we will get this value. And then you go for total final moments of these three, and that will gives me maximum moment at B 153.24 minus 153.24. Then we will go with, now this we know we are in position to find reactions. We will take moment about B0, and from this we are going to get value 126.36, 181.08, and maximum span moment for this we will get 145.42. And similarly we can find maximum moment for BC, and then we have this maximum moment X, we have 3 meters, and therefore we do not have maximum moment in this one. So maximum positive moment we do not have. We have this value as 153.24. Then we will go to the next condition, maximum span moment in AB. In this, wherever you have to find out maximum span moment, you have to apply total load on it, and on adjacent spans we have to go only dead load. So we have like this. So we have 27.9. And then we will go again with this same concept. We are going to be now on AB, we have total load, so minus 143.47. And here we have only dead load, so minus 20.93. Again, we are going to release it, so it becomes 0. Release this, becomes 0. Then we have to take carry over half of this. So now I will not explain of this. And in the same way, I will get this will be support moment at B, and from this we will calculate maximum span moment. We will find reactions by taking moment about B, shear force 0, and maximum span moment we will get as 146.39 kilonewton meter for AB. And similarly we will calculate for BC, and then for BC again we are going to get VC as minus, so we are going to be maximum span moment is negative again. So now we will go to the third condition. Now we have to apply total load on BC and dead load on AB, and then we will have a moment like this. So now here we have minus 118.38, here 24 minus 24.43, and likewise then make it 0 by releasing. So we have 0. Then we have to take carry over half values on these sides, and then we have to go for total moment, then distributed moment. So multiplying by distribution factors to total of this, we will get as final moments, and then we will find the maximum span moment, and we will get maximum span moment that is equal to, now we will have this as x 2.38, and we will get value of maximum span moment 6.45. Now in AB we have 146, and in BC 6.45, and at support B we have 153. And now we are going to find out depth from bending moment consideration. Maximum bending moment we have, that is at support, and therefore 153.24 into 10 raised to 6 upon 3.45 upon 230. Because at support we have rectangular beam. At support we have rectangular beam, and therefore we have to take value of B, that is 230 millimeters. And then we have this value 439.45, which is less than 450, and therefore okay. And then we can have this reinforcement for span AB. We will have BF L0 by 6 plus 6DF plus BW. Now L0 by 6 we have, L0 we have 4870. So we have to find out this value, that is distance between 0 bending moment, and then plus 6 into this is DF, and this is BW, and that will give me 1881.67 millimeters. And then substituting this, we will get value of AST for span AB 939.66. So change we have only, we have to put bending moment over here of that respective span or support. So we have 939.66. So we will provide 3 bars of 20, and then we will get it as 3 into 314, and that will give me 942, which is greater than 0.66. Here actually we have 0.14, and this goes to 42, which is greater than 939.66 millimeters square. Similarly, we can find for BC. So we have for span BC. Now here we have that value change. So 3000 minus 2260. We have calculated this value where bending moment is 0. And then we are in position to calculate this value. So plus 3 into 140 plus 230, it comes 1193.33. Here we have taken maximum span moment BC 6.45, and we will get this value 40.67 millimeter. We will provide 2 bars of 20 millimeter phi. Here you can find AST minimum. Here we are going to get 2 bars of 12 torque. We will provide. We have reinforcement for support moment. Now support moment we have seen 153.24. Now important, we have to take here BW, because support moment we have beam as rectangular, because we have tension on top and your slab goes in tension, so we do not have any flange width over here. And we will get AST, that is 1202, and we will provide 4 bars of 20 mm phi. So likewise we have to find the reinforcement for this. So this is all about of our continuous beam, and that is ABC by using moment distribution method. So thank you.